In today's lesson, what we want to be able to do is to show that shapes are similar. Most specifically, we're going to look at triangles. And there are two key ways to do this. We can either prove that all three angles are the same in a pair of triangles, or we can prove that all three sides are proportional to each other. So the first one, proving that interior angles are the same, is also referred to as proof by AAA, angle, angle, angle. The first example in your note looks something like this, where we have one triangle nested inside another. And we notice that they both have a 90 degrees and they both share a hypotenuse. So we want to prove that they are similar. So when we do a proof, first of all, we want to set out and say, this is what we're proving. And so I want to write down that I'm going to prove that triangle ABC is similar to, and notice this new little notation, it's like a little squiggle, it's called a tilde, is similar to DEC. It's not equal to, because they're not clones, they're not congruent figures, they're similar figures. Notice I'm also trying to label this triangle in such a way that the angles that are the same are listed in the same order. So angle A and angle D, which are these ones here, I want to prove are the same. Angles B and E, I want to show are the same. And angle C is the same in both cases. That one's going to be the easiest one to prove. So when I actually put out a formal proof, I'm going to begin with that one. Okay? So what I'm going to do is I'm going to say, first of all, the first angle that's the same as angle C in both cases. Okay? So I'm going to say angle ACB is equal to angle DCE. And I'm just going to choose to always do big triangle, little triangle. Big triangle, little triangle as it lines up in my proof statement as well. And then I'm going to give a reason for why that's true. And I'm going to say it's because it's a shared angle for both triangles. Okay, so there, I've proved the first angle of these two triangles is identical. Let's choose another one. Maybe we could choose this one that's a right angle because that's a little bit obvious, isn't it? Let's call this angle here ABC. So angle ABC is equal to angle DEC. And I'm going to give a reason for why I say that's true. I'm going to say it's because they are both 90 degrees. That was a little bit of a gift for us, wasn't it? So then the last angles that I have to prove are the same are angles A and D in the large triangle and the small triangle. I could call angle A BAC or CAB. I'm going to choose the first option, although it doesn't matter which one I use. But if I go BAC, right angle to A to C, I should do the same thing in the little triangle too. So I'm going to say it's equal to EDC. And the reason I'm going to do that is I'm going to go back to one of the things that we know exist in a triangle, and that all angles add up to 180 degrees. Therefore, if two of the angles are the same, the third one must be as well. So because if two angles are identical, the third one must be too. And you don't have to necessarily write this, but I'll put here, since all angles add to 180 degrees. And if you know two of them, the third one must also be identical. So there's an example of an angle, angle, angle proof using similar triangles. Let's do another one where the triangles are not nested inside of each other, but they have some parallel line properties that we can tap into to prove that they are the same. So again, we're going to look at an angle, angle, angle proof, and our picture looks something like this. We've got a set of parallel lines and two triangles. that are attached at a common vertex H. So in this proof, I want to begin with my proof statement. I'm going to set out to prove that triangle FGH is equal to, and because I ended with H, I'm going to end the next triangle with H as well. Or sorry, not equal to, it's similar to, my bad. Now, I don't know whether to begin with J or K, but I'll prove to you which one it should be. We're going to do KJH. And again, the reason is I want to show that angle F and angle K are the same. I want to show that angle G and angle J are the same. And I want to show that angle H in both triangles is the same. So, now we have to show the proof. Let's begin with F and K. So I'm going to set out to prove, and I'll use some short form notation this time. I want to show that angle F is equal to angle K. And I can prove that because of these parallel lines here and here. I notice that these angles are alternate. They are inside that letter Z that we looked at a few moments ago. Okay? So I can say they're equal because they are alternate. Okay, one down. Let's next prove that angle G is equal to angle J. And once again, we can do that because we notice that in those parallel lines, we have that letter Z pattern again, where we go down one parallel line across the transversal and out the other one, heading up, across, and up, or as we did before, down, across, and down. So that means, again, that G and J are equal because they are alternate angles. And then because we've proven that two of them are in fact identical, we can say that angle H here and angle H here are the same because again they all have to add up to 180. But we have another reason we could use here as well. We could say angle H is equal to angle H because we have that scenario of two lines that crisscross and we have angles across from each other that are opposite. So we can say they're equal because they are opposite angles. And there you go. Proof of similar triangles using angle, angle, angle. All right, the only other way we can prove that triangles are similar is by taking a different approach. In those first two examples we just did, we had no side lengths given to us whatsoever, so we were forced to use an angle proof. But if we are given a scenario of two triangles where some side lengths are given, it might be nice to see that they are similar in a different way, using some numbers this time. So this is called side, side, side proof, but you can only use it if you know the side lengths of all three sides for the pair of triangles you're trying to prove to be similar. So give me a second here just to recreate the image that you see. And we have a 30 and a 15 and a 20 and a 6 and an 8 and a 12. And I want to ask myself, are these similar? It's kind of hard to tell just by looking at them because there's been some flipping and translating around them. But what I want to do if I'm proving side-side proofs is the first thing I want to do is identify, I'm going to call it the Papa Bear side, or the side that has the largest value. And so when I look at these two triangles, I notice that 30 is the longest side length for this one, and 12 is the longest side length for this one. Let's now look for the Mama Bear sides. So we've got 20 here, and 8 here, and then finally we've got Baby Bear sides, 6 and 15. Now if we can show that one of these is a mini-me of the other, or one is the big brother or big sister of the other, that would be great. Now the only way we can do it is by comparing big to small. So I'm going to set up some ratios where I have the big triangle to the small triangle, and I'm going to compare their sides. So I have, for the largest ones, 30 to 12. For the mama bear ones, I have the larger one being 20, the other one being 8, and finally I have 15 compared to 6. Now, I want you to take a second to calculate the value of each of those. So what is 30 divided by 12? Well, I know it's somewhere between 2 and 3. It turns out to be 2.5. Lo and behold, if you do the calculation for all three of these sides, you recognize that they are all proportional to one another. In other words, the big triangle is 2.5 times bigger than the little triangle. Or you could say the little triangle is 2.5 times smaller than the large one. Okay, they're proportionate in every single way. And this has to be identical for the two triangles to be similar. Okay? Let's try another example. Oh, by the way, before I leave that, this value here of 2.5 is called the scale factor, and we will come back to that again. All right, almost there. If we go back up to the first example that we had for angle, 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 the one that looked like this. Could we prove it using side, side, sides? Well, the answer is no, because we don't have any numbers. But we could set up some equivalent ratios that could be used to find some unknown side lengths if we were given bits and pieces of values of side lengths for this diagram. So what would those be? In other words, if we were to compare big triangle, ABC, with little triangle, DEF, what would those side ratios look like? Well, I think we can see that because these two are right angles and they share a common base, they also have to be parallel to each other. So we could say that side AB is proportionate to side DE. And that would take care of these ones right here. The other sides that we can compare, because they're all going to have the same scale factor, would be looking maybe along this hypotenuse. So the large triangle has a side length of AC, the smaller one is DC. And then finally, on the bottom, BC for the big triangle is proportionate to EC. And they all equal K, or a constant, as I said to you, which is called the scale factor. So that's very useful in solving for unknown side lengths. Okay? We can do a similar thing with the other diagram that we had too, that we used to prove similarity through just angles. We can't put any numbers into it, but we could set up some proportions to show how the sides are related to one another. So I know that because these sides are parallel, I'm going to call this the big triangle, and I'm going to call this one the little one. In your notes, it looks a little bit more like that than it does in my diagram. These sides correspond to each other, so I could say that FG, the bigger side of the bigger triangle, can be compared to JK, the bigger side of the little triangle. I also know that this side and this side are related to each other. So I can say FH is proportional to HK, and GH is proportional to HJ, and they are all equal to some constant value. Okay. Lastly, let's go back to the example that we used to introduce side, 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 similar triangle proof one last time. And here it is.